So in this question, first we have to understand the question properly to continue with the answers. So a daily flight schedule is a list of all flights taking place that day. In a daily flight schedule, each flight FI has an origin city OCI and a destination city DCI, departure time DI and the arrival time AI, which is greater than the departure time. This is an example of a daily flight schedule for June 8, 2019, blah, blah, okay. And the format is given like that. If the flight 1, which departs from the Portland, arrives to Los Angeles, which departs on 7 a.m. and landed on 9 a.m. that day. Likewise, there are 6 flights which are scheduled from origin A to destination B. So first question. The question is, given any daily flight schedule, describe how to construct a DAG so that the path in the DAG represent possible sequences of connecting flights a person could take. What are the vertices and when are 2 vertices connected with the edge? Yeah, so the vertices are the flights, but obvious in the daily flight schedule. So we will have 6 vertices of 6 flight schedule mentioned in the question, and we will draw directed edge from flight I to flight J following the given constraint, like the destination of I should be equal to the origination of J, which means that flight J leaves from where flight I lands. So this is a common logic for the connected flights, that flight FJ leaves from where the flight FI lands. So where the first flight lands, the second flight should take off from that destination only. And the second constraint is A of I is less than or equal to D of J. So this is also an obvious condition, that flight FJ leaves after the flight FI lands. So the second flight should depart after the first flight land. So but obvious, the one can take connecting flight in this way only. So by following these 2 constraints, we can draw a directed graph, and we will draw the edges from the origin destination to the ending destination with the arrow pointing towards the end destination. And the second question is, why is our graph always a DAG? Yeah, so our graph is always a DAG because it's clearly a directed graph, and a cycle would be impossible, since that would require you to take the same flight more than once on a given day. So this is impossible, because once you have taken a flight, some time has elapsed and you cannot go back in the time to take the same flight again. Yeah, so it is also obvious that once you taken that flight, the same flight which you take from location A to destination B, then there is no provision again to go back to the same destination to the origin. Like, we have only flights in a cyclic direction, not in the acyclic direction. So that's why this case always be a DAG, because there won't be any cycle formed here. And so more formally we can say that the second explanation is given a little mathematical, or we can say logical, that we can say that if there is a cycle involving Fi and Fj, then there must be a directed path from Fi to Fj and from Fj to again Fi. What I told you guys now only. So then according to our definition of edges, a directed path from Fi to Fj means Ai less than or equal to Dj and Aj less than or equal to Di. Also by definition, Ai should greater than Di and Aj also greater than Dj. But then putting this together, we have Ai less than equal to Dj, less than equal to Aj, less than equal to Di. So this condition, which is a contradiction of the fact that Ai is greater than Di. You can see these four inequalities that if there is a cycle, then this condition will follow. Like the arrival of flight I is less than or equal to the departure of flight J, which is less than the arrival of flight J, and which is less than or equal to the departure of flight I. So, which contradicts that the fact that the arrival of first flight should always before than the departure of the first flight. So that's why this condition will contradict. So we can say that this is a DAG only. There is no cycle formed. There is no possibility of forming cycle in this example. The C part is what problem would you need to solve in your deck to help you determine the maximum number of flight a person could take on a given day. So since paths in the DAG represent possible sequences of connecting flights, the maximum number of flight a person could take is determined by the longest path in the graph. So once a traveler once he reach from destination A to destination B, his final destination, it means how much maximum flight he can take will depend on the path possible to reach his destination location from his origin location. So with the help of graph, we can determine that how much maximum flight he can take based on his origin location and the destination location. So it will depend on that. Means if his origin location is A and his destination location is B, and there is a direct flight to the location B, then there is a maximum only one flight that he can take. But if there are let's say there are 2 or 3 connecting flights between the origin location and the destination location, then there will be then he has to take 2 or 3 or maybe 4 flights. So how much maximum flights he can take will be variable and depend on the destination where he want to go. Draw the DAG you describe for the given example and give the maximum number of flight a person could take on that day. Yeah, so using the graph, so it will be more clear once you draw the graph for the question, and by drawing that graph, the longest path includes 4 flight, which is F2, F4, F5 and F6. So the maximum number of flight a person could take is on that day is 4. So 2, 4, 5, 6. So if we say a person take flight from Portland to Seattle, he reached Seattle at 9 a.m. Then there is a flight from Seattle to Los Angeles which depart from on 9:30 a.m. So here the both conditions are satisfied, which we saw in the first answer, that the departure time is greater than the arrival time of the first flight, and yes, the destination of first flight is equal to the origination of the second flight. Likewise, as we can say for the flight 5, it will depart from Los Angeles to San Francisco on 12 p.m. which is also greater than the 11:30 a.m., the arrival time of the flight 4. And same for the flight 6. It will depart from San Francisco to back to Portland, and it will depart on 1:30 p.m., which is also greater than the 1 p.m. So this is the longest path, like the maximum number of flights that one can take, return back to its origin and destination, which is Portland here in this case.